Good deal. So actually, kind of in concert or right in line with what Hilma was asking, the first thing I wanted to show you all today is that I can change the font size in HMS. I'm going to do that for you just so you can see the program better. But I'm going to point out the tools, program settings options here. So within program settings, there's a number of different things you can change. Most of these are fairly small, but there's a collection of things here. Font size is one of those, so I'm just going to change, for our session today, I'm going to change the font size to 14. And now, hopefully, everything just got a little bit easier to see. Now, there's a number of different settings here, like I said. One thing I've been playing with lately is light mode, dark mode. So HMS has a dark mode if you want that. That's right there. We have things like decimal separator, is period or a comma, those types of settings. State display language is something you might be interested in. And then decimal degree and latitude and longitude in decimal degree or degree minute second. I like using decimal degrees. If you've been doing engineering for a long time, maybe you're used to doing degree minute second style. So there's just a number of different settings here you should be aware of. Maybe take a look at that menu when you're playing around in HMS. I'm going to hit OK and accept that 14 font size. So everything's a little bit bigger for our session today. Hopefully you can see it okay. If not, like I said, I believe there's a setting in WebEx where you can do a zoom on my screen and what I'm displaying. All right, confirmation from Kuhn. You can indeed zoom in. So hopefully that's helpful for you. Okay. So this is the first, I call it the first workshop you did. I don't know. I think that's actually, what do we call it, module 2 or something like that. But it's the first workshop. So this is the model. You should all be familiar with this now. Should have gone through this. I'm just going to demonstrate a few things that might have been part of that and might not have. We talk about our different basin elements in HEC-HMS, and there's 7 of them, and we can add them graphically. Like if I wanted to add a sub-basin to my basin model, I can simply just add it here like that. That's how that works. I'm going to delete that sub-basin. Another thing is creating the hydrologic network and connecting elements. So I just want to demonstrate that for you. If I wanted to, right now Mahoning Creek Local, this subbasin, is connected to junction 2. If I wanted to disconnect that, I could delete that connection, and that connection is no longer there. If I wanted to make that connection again, I can do that graphically. So that's just with my mouse. I can click on this. And from the right-click menu, I can say connect downstream, and I can click on junction 2, and that connection is made. Now, another way that I can do that, let's go ahead and delete that connection. Another way I can achieve that same end is to do that from what we call the component editor. So if I select Mahoning Creek Local and go to the component editor, which is this editor in the bottom left of the software, I can select which element is downstream. And in this case, I want to set it to junction 2. Now, if I click in the map, it should update, and we see that connection's been made. So I think as part of the workshop, you did that graphically. I just wanted to show it can be done from the component editor as well, like I just showed. If I wanted to remove that connection, it would be simple as say none, hitting save. Okay. In practice, I use the component editor to make component connections more than I do the graphical editor. But we had to use the graphical editor just so you knew it could be done. Let me make that connection again. All right, my model is all connected. Now the next thing I want to do is link some observed data. I think we had a question about that. So I'm just going to show you how to create a discharge gauge. Right now we look at time series data and we have some preset gauges. Let's add a discharge gauge to this project. So I'm going components, create components, time series data. I'm just going to set this to discharge, and I believe the code for the gauge is PNXP, so I'm just going to add that for the name and create the gauge. You'll see in my time series data tree, that I now have a PNXP gauge. So that's good. Now what I need to do is just select that gauge in my component editor, or I said select the gauge. We need to point to a DSS file on my system. So I'm going to select single record HEC DSS, and I'm going to browse to that file right now. And that file is in my Punxsutawney project in the data subdirectory and this observed DSS file. So that's the file, and then I'm going to select the path, and it's just going to be the record that has flow as the C part in the DSS file. That's what that looks like. I've saved it. You notice that when things have changed, HMS uses blue text to indicate a change, and then once I save, it's gone to black text. Now I'm going to show you one thing that's special about file references is that this color, we have a different color scheme based on where that file is. Right now, this file is in my project directory. Let's just take a look at what an HMS project directory looks like on your machine. It should look something like this in the left. The Punxsutawney project contains a number of different files and subdirectories. One thing you can look for is a .hms file. So I know the .hms file is always going to be in the root of the project. And the project name is going to correspond to the HMS project name. Sorry, the folder name. The parent folder is just going to correspond to the HMS project name. So just to demonstrate this, my observe.dss is in this Punxsutawney data directory, which is a great place for that file to be. If I were to zip this project up right here at this level and say zip, all files would be internal to the project directory, and I could transfer that to a colleague who had a totally different folder structure, and all of the links would rectify. There would be no broken links if I were to zip that. Let me just show you for a minute. I put an observe DSS file, same exact file. I just put it external to my project. So if I went and linked that, which would be at the C temp observe, we're now outside of my project directory. So I'm going to make that change, and I'm going to hit the save button. You'll see that text just went to orange, which is our way of saying caution. So this will work on my computer. If I were to zip this project up and send it to another person, then this link is now broken. So that's why we're using orange text here as a caution indicator. I'm going to do one more thing. Let's just say I have a typo, and I delete the E at the end of observe, and I hit the save button. Now we have red text because this file doesn't exist. And if I were to run HMS, I might have problems with that. So that's just some visual cues to know whether your file references are valid or not. Another thing, if you want to look at all file references in a project, we have this nice file references table. So you can see here, these are all of the file references in this project. If I have a bigger project, this list gets really long. So this is just a good place to go and check where is all of my data, what files are they in. All right, let me browse to the, I want to be as correct as possible. So I'm going to browse to the file that is indeed in my project directory. Save. So I've created a discharge gauge, and what I'm going, this is considered shared component data, so it can be used for any basin model in my project. That's why it's called shared. But what I'm going to do is link it to this junction 2. So in the options tab for junction 2, I'm just going to select PNXP, hit save. So now I have observe flow for this junction. I'm going to go ahead and run the simulation. And now if I take a look at results of that junction, you see an observed flow, which is indicated in black, and then computed flow is this dark blue line. All right, another thing we typically do when we have observed flow is we demarcate what we call a computation point. So if you saw that, I just went to the right-click menu and said select computation point, and now that's red. And that is none other than a visual cue that I have observed flow at this location. So I can do that throughout my model. If I had observed flow at this subbasin, I could make it a computation point as well. And that just indicates to me and other modelers who might pick this model up in the future that I have observed flow there. And this is an area that I want to focus on for calibration. I don't have observed flow for Stump Creek, so I'm going to unselect that as a computation point. Just a right-click option, and it's none other than a visual cue. So I just wanted to point that out. All right. Now I want to show you global editors versus component editors, and part of that, just to demonstrate that, I'm going to set up a hypothetical scenario where I am going to make a copy of my basin model. And then for the copied basin model, I'm going to set losses, set no losses. And I'm going to use the global editor to do that. So let me just demonstrate that for you. I have this model set up. We've run a historical event, May 1996. And now let's, hypothetically speaking, I'm going to test this same event with just no losses and see how bad things could be. To do that, I'm going to create a copy of my basin model. And I'm just going to call it Punxsutawney no losses. So I've created a copy. It's that simple. Copied the entire basin model. Now what I want to do is set up a compute for this as well. So to do that, I'm just going to go through the create compute options here, and I'm going to call this May 1996 no losses. That's the name of that simulation. For this, I'm going to select my no losses basin model, and then same MET model and same control specifications. Now, one thing I will need to do for this is tell the MET model that I do indeed want to work with the no losses basin model. So that's a pretty simple change. I've made that change. Okay. Now, like I said, I wanted to demonstrate to you, in order to set no losses for all of these subbasins, I could go through the component editors one by one, and to zero out losses, it would look something like that. Now, if I want to do it for all elements in one editor, I'm just going to select the basin model, and I'm going to go parameters, loss, and then I select my loss method, and I get a nice global editor where I can see everything in one editor. So now I can zero out losses for all the components. And let's just take a look here, and I'll show you how this works. Like I said, I could do it from the component editor. Now, if I change the initial loss here, let's just say 1, I should see, we're at East Branch Mahoning Creek. If I set this to 1, I should see it update here. So let's just test that. Okay, it did. I went to 1. Let's go to 2, just in case that wasn't clear. I'm going to do it again. So I set my component editor to 2. This editor should update. It did. Good. So we're just 2 different editors to change the same exact parameters. I'm going to go back to 0, so I should see the component editor update here, and it did. That's good. So now I'm going to zero everything out, and to do that, I'm going to use this right-click fill option. It's pretty handy and does things quickly. I'm just going to do zeros. Okay, so now I should have 0 losses for this no losses basin model. Let me go ahead and run that simulation. Okay, good. That simulation has run. And now what I'm going to do is just show you that I can compare results between the two. So I'm going to expand the nodes for junction 2. Oops. And I'm going to select outflow for both my 1996 model and my no losses model. I'm going to hold down the control key, and I've selected both outflow time series, and you see a preview graph down here in the bottom left, and what I can actually do is I can pop that into its own graph. And so there I'm just comparing losses versus no losses for the May 1996 event. Now if I wanted to do something like if these blues look too similar and I want to change the look of those, I can actually edit properties for this line, and I can make it whatever I want it to be. Let's make it magenta and hit apply, so you can see that makes things stand out a little better where I can see the differances. So those options are available. Okay. The last thing I'll show you, I showed you the project directory, and you can look around through these files. I don't know how much we talked about last week, but there is this tool out there called HEC-DSS View, and I can't remember if it's part of the required software for this class or we listed it, but you might want to go out to the internet and download whatever the latest version is from our website. So DSS is HEC Data Storage System, and that's just how we store all of our data in HEC programs. And it's On my machine, I can tell a DSS file, well, file extensions, of course, but I can see this icon with a graph. So any of my simulations, like the May 1996 simulation I just ran, if I want to see all the output that's generated for that simulation, I can just open up this DSS file. Now, all of that output is available from HEC-HMS. I just wanted to show you that you could access it in HEC-DSS view. So I could do something like look at outflow at junction 2. So this is just directly accessing the HEC-DSS database. Okay, I think that's all I wanted to demonstrate. I'm going to put it to Matt. Is there anything else I should show while I have everything pulled up here, or any questions that came in for me?
Yeah, well, no questions in the chat, but do you have the open, the class page open, and can you go to the 6 questions that are in part 2?
Yes.
I have it open.
I also have a Kahoot quiz, and I don't know how different those questions are. How about, yeah, let's play Kahoot, and then if there's, Matt, track what we go over in Kahoot, and if there's things we need to cover, please bring that up.
Okay, can do.
All right. So please oblige me, if you will. I'm going to start this Kahoot quiz, and if you've never played, you're going to want to get your cell phone out and scan this QR code. And bear with me, I have never administered a Kahoot quiz, and I want to give it a try. We've used it on a few classes, so we'll see how this goes. We got one in. Okay, good. It's working so far. Give it a minute or so for folks to come in. I see a little bit of, well, while folks are coming into Kahoot, I see a little bit of traffic in the chat about continuous simulation. So that's, I believe that's actually one of our questions. But so it is timely. If you did watch that introduction series of videos, HEC-HMS can do both event and continuous simulation. And everything's, we were talking with a colleague yesterday in Brazil asking about doing a long-term water balance for a large basin and whether HMS was up to the task or not. And the answer to that, we told them absolutely yes. All of the processes are there to do that type of simulation. So it's a matter, the thing you get into with continuous simulation is you need to model the entire water balance, and evapotranspiration is a heavy component of that. So near almost a good portion of all the precip that falls goes back into the atmosphere as evapotranspiration. So anyway, if you are doing continuous simulation, it's very important to set evapotranspiration up and set up a basin model that uses a loss method that tracks soil moisture state, because now we can't just say losses are lost and that's the end of it. We need to actually track what the moisture state is in the soil so we know so we keep a water balance essentially. We can talk more about that if we need to, but that's a good question. It's actually something we cover more in depth in our advanced class, all of those evapotranspiration methods and continuous loss methods. Okay, in the interest of time, I'm going to start our Kahoot in about 10 seconds, so last chance to get in. I see people are still coming in. I wish I had more time to kind of let you come in, but we got to keep moving for our class. All right, let's give this a try. I'm going to go ahead and start the Kahoot and see how this goes. True or false? HEC-HMS can be used for a long-term continuous simulation. That was a timely question. Okay, I think and I hope that it looks like we have 23 answers, which is good. I hope that if I hit the skip button that it doesn't just skip it entirely, but it collects those answers. It tracks those answers that we have. So I don't want to go the full 60 seconds. Okay, yep, that's right. So it worked like I thought it would, and we have 23 answers, and all answers are correct. That is true. HEC, like I just talked about, HEC-HMS can be used for continuous simulation. Good job. And there's a scoreboard. So the only thing at stake here is pride, because I cannot. When we do these classes or we do these quizzes in person, often there's things like candy or small trophies on the line. But since we're doing this digitally, maybe I can send you a digital candy bar. It just won't taste as good as the one in person. So, all right, moving on. The 7 different types of hydrologic elements in HEC-HMS are. So pay close attention to the element types. Think about what each one is. We talked a little bit about that. All right, I'm going to give it 5 more seconds. Got 17 answers in. All right, looks like most folks got that right. Just little differences in naming there. Like the first answer has basin in there, and basin isn't actually a hydrologic element. The basin is where you apply or build a network of hydrologic elements. So the hydrologic elements are subbasin, reach, reservoirs. They're the 3 most common. Well, sorry, subbasins, reaches, and junctions I would say are the most common, but there's also reservoirs, diversions, sources, and sinks. So those are 7 hydrologic element types. And when you put all those in a model and build a network, that constitutes a hydrologic model. Let's look at our score. All right. Looks like Josue is our new leader. Project directory is C project punks. Where should I store a HEC DSS file with time series data to use in my project? Talked a good bit about where to store things to be kind to your coworkers who you might be sharing a project with. Talked about the color coding for internal and external. All right, 5 seconds. All right. Good. It looks like most of you got that right. So out of all the directories that you see here, C Project Punk's data is internal to our project directory, and that's the important thing because then we can share that project if we were to zip it up. We've added that data subdirectory intentionally for you to place data in. That was kind of a cue to users, put your data here. So that's a great place to put your data. And scoreboard, Josue still on top, good job. A simulation run is the combination of yeah, sorry if you can't get in. Please do pay attention, but once the game is started, that's it. So anyway, do pay attention to the questions. I think it'll help you when you go to answer the questions in the course. All right, I'm going to give it 5 more seconds on this. Okay. A simulation run is a combination of a MET model, a basin model, and control specifications. So MET model is our boundary conditions. Basin model is the basin and the state that we want to model it. Like we could model a historic state like we did in this example for May 1996. And then I also had a copied basin model where I just tested no losses, but we're just combining MET model, basin model, and then control specifications is the temporal extent and the resolution. So control specifications say things like, I want to run from this state to this state, and I want to use a time step of 1 hour or 15 minutes or 1 minute. So that's what control specifications are. All right, this way still on top. Got 1 or 2 more questions. 5 out of 6. What type of results are available in HEC-HMS? I didn't go over that so much in my demo, but I know it was in the course content. So hopefully you picked up on that. Okay, that one had a short timer, so you had to answer fast. The answer, oh, that was multiple select. I should have told you that. So that quiz question, you could answer, you could select more than one. So maybe that threw some of you off. Sorry about that. But anyway, the answer is all of the above. We have tables with time series data. We have what we call summary tables, where we can view things like the peak flows, timing of peak flows. We can look at calibration metrics like Nash cliff efficiency. We have what we call element graphs, which is just things like the flow hydrograph for a particular element, and then spatial results, which is a special kind of results where we can see what happened in space, which is a cool thing. We'll demo that at some point this week. I don't think we'll have time today. But we need to go into the spatial world to demonstrate that, and we're not. We'll be spatial when Matt does his demo. All right. Let's see here. Sorry again for the not explaining the multiple select. We did have a mix-up on the leaderboard there. Nuri, you're now on top. Let's go to the final question. What type of simulation computes frequency storm flows from multiple locations in a basin? So hopefully you paid attention to the video presentations, because I did not demonstrate that just now. This is a special type of simulation that we use with frequency storm and hypothetical storm in HEC-HMS. And we can do depth area reductions from multiple locations. All right. 5 seconds. We got 20 answers in. See who comes. This is the last question of this quiz. Okay. See how depth area analysis is the correct answer. I kind of hinted at that as I was talking, where we can do depth area reductions from multiple locations. So that is the analysis type if you were interested in that. And that's another thing we don't cover so much detail in the basic course. It's something that's more of an advanced topic. If you want to know more about it, there's plenty of resources out there on the internet if that's something that's of interest to you. But we're just really emphasizing here that HMS has many different simulation types that are kind of tuned for different purposes. You'll be using the simulation run the most this week, and then that's most commonly the simulation type we use. We do have a forecasting alternative that I talked about some of the video that's near and dear to Matt's heart now, so that just allows you to combine things from the most recent past with projected future precipitation, that kind of thing.
So now let's jump to part 3. And the way I'll kick it off here is what Tom was showing you was you can use HMS without really defining the geospatial layout of the watershed, right? So if you have an idea for your subbasin area and you have other information that helps you estimate parameters for that watershed, well, you could create a simple, what we call a stick figure watershed, where the elements don't have a true geographic location identified with them. It's just a very simple model. And sometimes those are really useful, right? So you want to set up a model quickly, you have some basic data, and you need a really quick answer. So yeah, you can use the non-geospatial option. What we're going to talk about now is HMS has an integrated GIS component within the software. You don't have to rely on a third-party GIS tool. You can do all of your, or let me say it differently. You can do most of your GIS processing within the HMS software. You will have to find terrain data yourself. So there's a number of websites out there where you can download terrain data. What I wanted to point out real quick, and I'll put it in the chat. Let's put it in the chat now. So chat. There. All right, so this link that I put into the chat, that's going to take you to our GIS tutorials and guides. And the two to look out for are right here. Preparing terrain data using ArcMap, preparing terrain data using QGIS. If you don't have ArcMap or you can't afford the license, you can use QGIS. It's a free piece of GIS software. And then this tutorial walks you step by step of after you download the terrain data to your computer, you can process it to get it ready to use an HMS. Okay, what I'm going to talk about now is let's assume that we have the terrain data, it is ready to use. Okay, so let me pull over HMS here. Look, there's nothing in my model. It's a brand new model. Just like creating basin models and meteorologic models, the workflow to add your terrain data is you open up the terrain data manager, click new. There's the name of my terrain. I'm going to locate the GeoTIFF file that's already on my computer. Let's see here. It's on my desktop. Let's find it. Let's see. I know the vertical units for my terrain are in feet. So you do need to be careful with the vertical units. Make sure that you understand what the vertical units are. And one thing too, a word of caution, make sure you know the projection of your terrain data. My recommendation is always work with a projected terrain data set. Most of the time when you grab or download the terrain to your computer, it's unprojected. It's in geographic coordinates. And what I would recommend is use a GIS tool like QGIS or ArcPro and reproject that to something like UTM or some common projection that you are used to. All right, so I've loaded in the terrain data. It's right there in the water. This is our Watershed Explorer, so that's the terminology that I'm going to use. It's just like your Windows File Explorer, but we're going to explore watershed information here. Now I'm going to go back to the components menu and create my basin model. So I'm going to open the basin model manager, click new. I'm just going to accept the default name for now and click create. Okay, so you notice the very first time that you open an empty basin model, there is nothing in the project. There's no terrain data associated with it. It's a very empty watershed model. So the first thing I'm going to do is select the terrain, hit the Save Project button. This menu or this window that opens right now is asking me whether I want to define the projection for the basin model first before I import the terrain, or if I want to use the projection of the terrain to set my basin model. And that's the step that I'm going to use. I'm going to choose skip. And what that means is it's going to take my terrain's projection and apply that to the basin model. And there we go. There's my terrain data set. Oftentimes you need other geographic information to help you with your model, right? And so what I have done, and this follows the best practice that Tom was talking about just a minute ago. So this is the directory of the project that I just created. Here's all the folders and files that HMS created. And what I did inside of the maps folder, right here, I copied other shape files, geographic or GIS shape files, into this project directory. So I want this information to be completely contained inside my project directory. Okay, so once you have those shape files in your project directory, you can add those to your basin model map. And that's what I'm going to do next. I'm going to go to the View menu, choose map layers. And I'm going to add. So let's add those new map layers. All right. You can add one at a time. So the first map layer that I want to add are my rain gauges. Here we go. You can modify the draw properties because right now I can barely see those rain gauges. I'm sure you're having a hard time too. So let's click draw properties. Let's change the size for those. I'm going to change it from dark magenta to red. And then the style, I like to use diamonds for my rain gauges. And click apply. There we go. So there's my 3 rain gauges for the project right there. Another layer that I like to add most of the time is a stream network. There's this layer called NHD Rivers. I'm going to add that one. So you can kind of see the poly lines for the rivers. I'm going to change the draw properties. Change it to blue, and let's change the weight, make it the lines a little bit thicker, and then click apply. There we go. Almost done. The last layer that I want to add is my stream gauge layer. So if I have observed stream gauges, I usually bring those into my project to help me because that's where I want to make sure that I delineate the sub-basin outlet to that flow gauge. I'm going to click add and choose flow gauges. There. You probably won't see it in the map because I think it falls right below that precipitation gauge. So let's change the draw properties of it real quick. We'll use black. Let's change the size to 25, something really big. There it is. So it's down there. All right. So I usually bring in those GIS layers. After you have all the GIS information in your project, the next thing you can start doing is, if we go to the GIS menu, and there's the processing steps that you typically follow. Terrain reconditioning, I'm not going to go into too much detail today, but terrain reconditioning, this is basically what you would use to burn in the stream network. So for example, let's just say that this terrain data set, maybe it doesn't follow the natural drainage, right? Maybe the resolution of the terrain is not fine enough to capture how water moves across the terrain. So what you can do is use the terrain reconditioning tool to burn in these blue streams into the terrain. And what I mean is the program has a function where whatever grid cells fall below these stream lines, it's going to lower the elevation based on whatever lowering value you define. And so it's artificially creating this stream network into the terrain data set. It's burning it in. You can also build walls. So if you have your published sub-basin boundaries and you want to add those to the project and make sure that the terrain exactly follows existing delineation, you can bring those in as walls and add that information to the terrain. Okay, so I'm not going to click on terrain reconditioning today. You can read more about it, but basically those are the 2 steps. You're going to add walls or burn in streams to your terrain data set. What I am going to talk about is pre-processed sinks. So I'm going to go ahead and click that. It should be really quick. If it's not really quick, then there's a trick that you should, or there's a nice little feature here under the tools menu, program settings, and it should be under defaults, number of cores. So by default, whenever you add HMS to your computer the very first time, the number of cores will be set to 1. You can open up this editor and change the number of cores to whatever's on your computer, right? So if you want to go up to the maximum, you can go up to the maximum. And what that means is for these GIS steps that you run through, the program's going to make use of more processors on your computer. So they should be faster. So if these GIS steps are slow, then add more cores to HMS or make them more available to HMS. Okay. We ran fill sinks, and what does fill sinks do? Well, let's kind of zoom in here and see what we have going on. You should see these blue cells, and what those indicate are grid cells where HMS said water is not moving across the terrain. These are pits or low points in the terrain, and HMS has to raise the elevation of those grid cells so that water can completely flow across the terrain. So those are what we call sinks or low spots. The program's going to fill the elevation up to the minimum of the 8 surrounding grid cells. Okay. So now what we have, if you go back to the view menu and choose map layers, you see the sink fill terrain right here. So this is the terrain that is what we call a hydrologically corrected terrain. Water is going to flow across the terrain to the outlet of the watershed. Okay. The next step after you have a hydrologically corrected terrain is to run pre-processed drainage. This should be relatively quick as well. So a couple of things are going on in this step. You can see the byproduct. Let's look at the byproduct here. So I know it's a little interesting to look at initially, but we're looking at, this is the flow accumulation grid. And what that means is that algorithm goes through, first it computes the flow direction. So what's the direction of the steepest slope from grid cell to grid cell? And once we know the direction of the steepest slope, then we can start accumulating upstream grid cells, right? So let me show you this nice little feature. So if you select flow accumulation in this editor right here, your map layers editor, oops, I turned it off. There we go. And then if you hover your mouse in the map, you should see a tooltip. That tooltip right there says 33. That is the number of upstream grid cells that flow into that grid cell, right? So for these that are lighter shading, these are the grid cells that are along the subbasin boundary, right? So there's no upstream grid cells that flow into that grid cell. But as we work our way downstream, and I'm on the stream network, there we go. So 1,897 grid cells are upstream of the one where my mouse was located right there, okay? You can get more information about this. This is one of those lectures that was included in part 3, but this is the slide to pay attention to for that lecture, because this really walks through, here's your elevation model, your terrain. Here's the flow direction grid, so the direction that water flows based on the steepest slope. And once we know the flow direction grid, then we can compute the flow accumulation information, okay? So let me zoom out. What you can really see from the flow accumulation grid is you can get a really good idea of what your stream network looks like, right? And so what I notice when I look at this is my network doesn't exactly follow that blue line, which is okay. If I burn the blue line into the terrain, then it would exactly match it, but you don't have to make it perfect for this. Okay, so we have flow accumulation and flow direction. Now we can go to identify streams. And I know there was a discussion question about identify streams. Before I jump into it, let me turn off some of these layers to make it easy to see here. There we go. Okay. All right, so let's just experiment with identify streams. Here we go. So it gave me an area to define the streams as 16 square miles. Let's just choose the default for now. So I'm going to hit OK. I am going to turn off my blue streams. There we go. And let's turn on identify streams. There we go. I know it's going to be hard to see. You might have to zoom in pretty well. What's happening is HMS does not define a stream until there's at least 16 square miles of drainage to a point, right? And so if I define 16 square miles as my threshold to identify a stream, then I'm going to get a specific delineation based on that threshold. So let me zoom back out. There we go. So let's just do it. Let's learn this way. So I define 16 square miles. Next step that I need to do is define my breakpoint. The breakpoint for most applications is going to be the most downstream point in the watershed. So for me, it's where my gauge is located down here. So I'm going to define my breakpoint right there. On this, it has to be on the stream network. I'm going to call it outlet. All right. And now let's get our first delineation, the first sub-basin delineation here. All right. So these subbasins, these are based on a stream threshold of 16 square miles. If this is too coarse, if these subbasins are too large, then what you can do, you can always back it up. So let's go back to identify streams. Yes. And if I change my stream threshold from 16, let's go down to 5 square miles. You could see it. I know you can't. The identify streams layer is much more detailed now. So I'm going to have many more subbasins than I did before. Go back to GIS and choose delineate elements. Now you should notice 2 or 3 times more subbasins in the model, right? So you can see these smaller subbasins have been added. So I'll pause for just a second. Any questions, or does anybody have any input why or how you would choose a stream threshold for your project?
There's actually a question that just came into the chat, and I hope it's Lincoln who posted that. I hope what Matt just posed, I think, is exactly what you're asking. So Matt's asking, what is well, state it again, Matt. I don't want to get it wrong.
Yeah. So how do you choose a stream threshold? You've been given the job of creating a watershed model. And how do you choose how many subbasins should exist in the model? Because the choice that you make here at this point in the modeling process has impacts throughout the rest of the model, right? So do you want a model that has 20 subbasins, or do you want a model that has 200 subbasins?
So if anybody wants input, feel free to come off mute. We'll take verbal responses on this one. Anybody? Everyone's shy today.
That's okay. All right, well, I'll give you my 2 cents. And then if you have additional thoughts, just come off mute and you can join the conversation too, or put it in the chat. Let's see here. Let's see, how should we start this?
That's a good discussion. A good answer came in. A model should only be as complex as it needs to be, and that goes for more than just delineation.
Mm-hmm. Yep, that's a really good point. So one of the things I commonly say at this point is keep it simple, right? So you want to start with a simple as simple of a model initially, and then add complexity as needed, right? And so for this watershed that we're looking at right now, we have this drainage area. There's only one location down here that has observed flow, right? So for the simplest of models, the simplest of models would be just one subbasin here that's generating flow for that outlet, right? But let's say I'm doing some kind of inundation mapping. I want to map a floodplain. And I know that my floodplain starts from about right here where my mouse is at, if you can see it, and it goes downstream to the outlet. So in that case, since I'm trying to define the floodplain, I need to make sure that I have boundary condition data coming in at the upstream end, and then I need additional flow information throughout the floodplain. So in that case, I could get away with a model that has one subbasin upstream of the boundary condition for my hydraulics model, and then a couple of subbasins downstream. So it really depends on how you're going to apply the model for prediction. So that's those are really the two things that I like to keep in the back of my mind. Keep it simple and make sure you understand how the model is going to be applied.
Good comment from Roger in the chat, just considering things like vegetation type, cover, geology, impervious area. Those are all things that are worth considering. I think, like Matt was saying, my primary concerns when I delineate, when I first start, are where are my gauges and where are my structures. Those are the first two things that I think of, and then outside of that, I start going down the list. Oh, is this an urban area? Well, obviously the infiltration properties or the nature of infiltration for that urban area is going to be a little different than the countryside, and so I probably want that to be its own subbasin. Subbasin just captures is you get to use uniform properties across the subbasin. Now I know in the sense of gridded we could discretize that further, but that's kind of the idea. You want to capture differences throughout your subbasin or throughout your modeling domain with your subbasins.
Right. Yep. So that's the third piece of it too is how does the watershed conditions vary, right? So if you have a steeper portion of the watershed, different soil types, land use, you name it, then you might want to discretize or have a subbasin that captures that different or heterogeneous area.
Matthew, may I propose another question, just in the same sense?
Go for it.
Just to keep the question in the same subject, but in the case, as Eric mentioned here, it depends on the outlet and any structures that are important in the basin. And in this case, that perhaps you have a bridge or a dam that is constructed about a third upstream in the Seafood River. So if you suppose that around there we had another kind of structure, can I define the basin exactly there? And perhaps I'll have two subbasins of different sizes instead of having this limitation of sizes as we just saw Thomas drawing there.
Right. Yep. Let's go there next. So that's a perfect segue into what I want to talk about next. Is let's assume that we're going to use this model, this HMS model, to pass information to our river hydraulics, or HEC RAS model. And the RAS model, it starts right here where my mouse is at, and it goes downstream to the outlet. There's going to be bridges, there's going to be all kinds of structures along that reach. So let's go through a certain way of how we could delineate this watershed to keep it simple and provide information to the RAS model. Okay, so the first thing is I want to merge these subbasins upstream. So there's no reason to have multiple small subbasins here because I have no observed flow information to calibrate to. So I'm going to just select these. So you can hold down the Shift key and select these subbasins. You might have to zoom in to make sure you grab those really small ones. So there we go. These subbasins should be adjacent to one another. And if they are, and I go to the GIS menu, then I should be able to choose merge. It doesn't look like they're adjacent. So let me try.
At the very bottom there, below your mouse.
Oh, sometimes let's just do a few at a time to make sure. So GIS merge, there we go. Let's merge those. Zoom back in. So we want to merge that one and that one. And should be that one.
You need 5,
Okay, so
5 down below. Yeah.
Yep. Thank you. Let's merge those. All right. So now we have one subbasin for the upstream end of the watershed. We're going to take the flow from this subbasin, pass it into this reach, or also pass it into our river hydraulics model. You notice there's a tributary over here, right? So this is a fairly large tributary. I want to keep it separately or separate. I don't want to merge all of these subbasins along with the other ones because let's just assume there's a bridge in our river hydraulics model. And we want to make sure that we're capturing the flow from that tributary and feeding it to the river hydraulics model. So I'm going to merge just these subbasins right here together. There we go. Okay, and now you notice there's a number of subbasins in what I call the local area. The local area is downstream of your upstream portion of the watershed, and it's kind of in between. You could merge some of these together if you wanted to. So we could merge these three right here. And then we could merge these three right here. All right. The river reaches, those are separate segments. You can merge river reaches together as well, right? So same process as merging subbasins. You hold down the shift key, select the river reach, then select multiple reaches and go to the GIS menu and merge. Okay. And then the last thing, sometimes you work on a delineation and then somebody says, oh, hey, Matt, did you realize that there's observed flow in the watershed? Maybe there's a gauge somewhere up here, right? And you're like, oh, no, I need to redefine my subbasin delineation. Well, what you can do is you can always delineate at any point in your watershed domain, right? And so what I like to do whenever I do a delineation is turn on my flow accumulation grid. Let's turn that on. So let's just assume that there's a gauge somewhere in this area. So I turn on my flow accumulation grid. I make sure that I can find the stream network. So my stream network should be right here. And we can
actually, Matt,
oh,
turn off identified streams, because I think that's a different color.
Oh,
yeah, turn that one. There you go.
Yep. All right, let's use this point down here then. All right, so now I'm going to delineate a new point, a new subbasin outlet. So if I go to GIS, see, that's the breakpoint. Oh, you gotta select the subbasin first. So I have that subbasin selected, and then if I go to GIS, delineate, split subbasin. Sorry. Split subbasin, you should notice the mouse pointer changes to the crosshair, and then you just locate the location where you want to delineate the new subbasin. I want to make sure I'm in the right spot. Yep. Okay. And the hard part here is you want to make sure you click on your stream network. So I'm going to click on the stream network right there. Accept. So now we have, let's turn off flow direction or flow accumulation. So now we have this upper subbasin. So we can, if we have observed flow, we can calibrate the model or just this subbasin to that observed flow. And then we have these other subbasins throughout the domain. So don't get upset if you merge subbasins together and then you realize you have to split. It's very easy to split the watershed. Or if you have too many subbasins, it's very easy to merge those subbasins and reaches together. Okay? So let me pause there and see if there's any other questions. You can come off mute if you want to. All right, the last thing that I'll show before I jump into the discussion questions, you can always check to make sure that elements are hydrologically connected to one another, right? And so the way that I do that is I right-click on my basin model, and if I choose resort elements hydrologically, what that should do is now the list that you see in the Watershed Explorer should show you from the most hydrologically remote portion of the watershed. So this is the headwaters, and you can click on each of these elements and work your way to the outlet of the watershed. So there's the reach, there's the next subbasin, there's the next reach, and so on. Okay, so this should be the lowest, the outlet of the watershed should be at the bottom, and the headwater subbasin should be at the top. let's say you go through these steps and you don't like the default names. I would always suggest that you change these names. Don't accept the default, customize the names. So for example, it's very easy to change the name. What you can do is you can right click and choose rename, and then just type the new name right here. I'm gonna call it Matt's Subbasin. Okay. So please customize your names. You can change the names for any of the hydrologic elements, right? So any of the subbasins, the reaches, the junctions, you can change those names.
Do Matt, demo or right click on Basin 1, and there should be an option to rename them all, which is pretty cool. So Basin 1 node, rename basin elements. Down one below that. There you go. So there you can actually one table to rename them all. It's a newer feature, so good one to see.
See, I did not know about that. I learned something new today. Let's see. Apply. Okay. Yep, there's Tom's reach right there. Okay. That's pretty cool. I like that. All right, let me pause. Let's see if there's any questions in the chat.